Introduction. I wish to thank John Kim and all the organizers for organizing this nice conference, and special thanks to John Locke for inviting me, which is great, and thanks also for the dinner, which was really great yesterday, and I see that many people are still there. So there are quite a few domains in which Boolean functions, that is read-Muller codes, play a role in cryptography. At least I see 3 of them, but maybe there are others. The first one is the design of substitution boxes in block ciphers. The second is what presented yesterday Patrick Solé, which is a recent topic, where we use Boolean functions for side channel attacks, countermeasures to side channel attacks. And the third one is Boolean functions in stream ciphers, and this is the subject of my talk. So I'll give some reminders on the topic, especially on the algebraic attacks, which came at the beginning of this century, and recall what is known on functions allowing resistance to these attacks, and then I'll spend more time on recent developments. So what is a stream cipher? It's based on the principle of the one-time pad, in which you just add to the plain text a key stream to get the ciphertext, and at the receiver end you take the ciphertext, you add the same key stream, and you get back the plain text. And since your key is something that like 120 bits, 120 bit long, and the key stream should have the same length as the plain text, which is maybe 1 megabits. Then you have to build the key stream from the key, and this is the pseudo-random generator which does it. So a pseudo-random generator is supposed to build a pseudo-random sequence which has many properties of real random sequences, but obviously not all, and which must resist all the known attacks. Every PRG, such PRG, is made of a linear part, because what is linear is fast, and stream ciphers must be very fast. In cryptography, speed is maybe the most important. For instance, the AES won the contest because of speed, not because of robustness. All the candidates were robust. All those which went to the end of the contest, and the one which won was the fastest. So we need to be fast, and linearity is the solution to it. But linearity, all that is linear, is weak against attacks. So you need also a nonlinear part, and often the nonlinear part is made by a Boolean function. So a Boolean function from f2 to the n to f2. There are mainly 2 models for using the Boolean function to make this nonlinear part. These models both use the linear feedback shift registers as the linear part, and so they come after this linear part. Linear feedback shift register is some device which is very simple, especially in hardware, and which outputs linear recurring sequences of this form. Okay? It's all that you have to know about LFSRs is that they produce linear recurring sequences. In the first model of using Boolean functions, you have several LFSRs. At each clock cycle, each one outputs 1 bit. So at each clock cycle, you have n bits, if there are n LFSRs, and these n bits are the input to the function, which outputs 1 bit. So at each clock cycle you get 1 bit of the key stream. And so if you want a key stream of 1 megabits, you have to run it during a million of clock cycles. And the other model uses, instead of using n LFSRs, it uses a single LFSR. And thanks to the fact that there is only one LFSR, this LFSR will be much longer. This LFSR maybe will have length 256. Okay. While the others maybe were 20 bit long. And the input to the function is taken directly inside the LFSR. Okay? And the principle is the same. At each clock cycle, you get 1 bit of the key stream. In both models, the function must be balanced. That is, the probability of output of 0 and 1 must be equal. Otherwise, there will be a bias, and you can use it at least for distinguishing when a pair of two text is a pair of plain text ciphertext. And we don't want that in cryptography. Okay, so it's the first condition, function balanced. But there are many other conditions. So your coders, you know about the read-mode code, so I don't have to develop about the algebraic normal form of Boolean functions. It's a polynomial representation which is unique, exists and is unique, and so its global degree is called the algebraic degree of the function. And this algebraic degree is related to at least 2 attacks. The very old Burle-Massey attack and the more recent Ron-Jean-Melesset attack. And both of these attacks work when the algebraic degree of the function is too low. So we will need the functions to have high algebraic degree as well, and balanced. The affine functions are the worst possible functions from algebraic degree viewpoint. They can always be represented in the form of an inner product between a constant vector and the input plus a bit. The inner product is defined here. And of course, the set of these functions is the read-mode code of order 1. But this representation, which normally should suffice because all that plays a role in crypto is linear, is with respect to the linear structure, vector space structure, is not enough to design functions. We need to use more structure often to build good functions. So to have more structure, a way is to use the field structure. So the vector space, as a vector space, f2 to the n, is endowed with the structure of the field f2 to the n. I guess that everybody knows in the room how we do. There are many ways. You choose an irreducible polynomial, or you know that this is a vector space of dimension n, and you take a basis. Anyone will fit. And then any function from this field to itself admits a unique representation again, but it's again a polynomial representation, but there are 2 main differences. The first is that the coefficients are in the big field, not in f2. In the algebraic normal form, the coefficients were in f2. Here, they are in the big field. And it's univariate, only one variable, x, which ranges over the big field. And the condition for having existence and uniqueness is that the degree of the polynomial is at most 2 to the n minus 1. It's very simple. What is a Boolean function? It's a function from f2 to the n, the big field, to the prime field f2. And the prime field f2 is a subfield of f2 to the n. So it's particular function from f2 to the n to f2 to the n. What is particular to Boolean functions? Two things. First, the two extreme coefficients in this polynomial. The two extreme coefficients must be in f2, and for the others, they are in the big field, but a sub 2j is equal to aj squared, where j is viewed mod 2 to the n minus 1. Okay. And this allows, for instance, a Boolean function to be represented at the trace of some polynomial, where the trace is the well-known function. A word about that. This does not allow uniqueness of representation, while this allows uniqueness of representation. If you want to have uniqueness here, you cannot take just the general trace. You have to be more precise and to use subtraces. I don't use it here, but just know that sometimes we need to be more complex here to get uniqueness if we want it, but I don't need it here. Anyway, so this was just a remark, but any Boolean function can be represented in this way, and we have coefficients, and the algebraic degree nicely expresses by means of this representation. It's the maximum two-weight of the exponents with non-zero coefficients, where the two-weight is just the weight, the Hamming weight of the binary representation. Okay, for instance, the two-weight of 8 is 1, because 8 is 2 to the 3. The two-weight of 3 is 2, because 3 is 2 plus 1. Okay, and the affine functions can be also very simply represented in a unique way for these ones. I need the Walsh Transform to study the functions. So what is the Walsh Transform? We've seen it in previous talks. Since we can live in the vector space or in the field, I give the two expressions. In general, in the vector space, which is the weakest structure, so more general, you define the sum. We calculate in z the sum of minus 1 to the f of x plus a dot x. I defined the inner product in a previous slide. You can take here any inner product. You can take the inner product I've introduced. You can take any other one. It will take a slightly different Walsh transform, but all the properties of the Walsh transform will stand. In the particular case of the field, then you can take for inner product trace of the product. It's the natural inner product in this structure. I'll need also the Hamming distance between two functions, but you know what it is. Since you know real model codes, it's just the distance between the corresponding vectors of length 2 to the n. And this allows defining the nonlinearity of a Boolean function, which is the minimum distance between the function and all affine functions. But it can be very simply expressed by means of the Walsh transform. The nonlinearity equals 2 to the n minus 1 minus the half maximum magnitude of the values of the Walsh transform. And thanks to this property and to the well-known Parseval relation, the Walsh transform is a Fourier transform, so it has a Parseval relation. And this Parseval relation directly gives that the nonlinearity is upper bounded by 2 to the n minus 1 minus 2 to the n over 2 minus 1, whatever is the parity of n. And the functions which achieve this upper bound with equality exist, obviously for n even, because for n odd this is not an integer, and they are called bent, and they are a subject of study of their own, because they are related to different sets and many other things.
What is f hat here?
F hat is, yes, it's the Walsh transform. Okay? So the nonlinearity also must be large. This is to prevent from an attack called the fast correlation attack. And there are many versions of this fast correlation attack, but in all the versions you need the nonlinearity to be large. So at this point we have already three conditions: balanced, large algebraic degree, and large nonlinearity. Three things. And what is specific to the study of Boolean functions in crypto is that you have all this list of conditions, and if you find a function which is great for almost all conditions but one, for instance, you can put it in the basket. It cannot be used because it's weak against an attack, and you want to be strong against all attacks. Okay, so until the end of the last century, roughly, this was enough. You needed balancedness, high algebraic degree, large nonlinearity, and you could get this with functions of, say, 10 variables. And things changed in 2003. In 2003 came algebraic attacks. The idea of algebraic attacks was old. It was already mentioned in the Shannon paper on crypto, so it can hardly be older. The idea is very simple. You have a crypto system. You can translate any specification of the system into an equation, into equations. And equations whose unknowns are, for instance, the key bits. And if you can solve the system, you find the key bits, so you've broken the system. And so every crypto system should lead to a system of equations which is not solvable in at least 1 million years. Okay. And so it was just an observation by Shannon, because this means that, in fact, if you look at all the crypto systems, they work like that. The associated systems of equations are indeed unsolvable. But a very nice idea, four-stream ciphers, was found by Meyer and Courtois. They observed that if you call S0, Sn-1, for instance, the initialization of the linear part of the pseudo-random generator. So this linear part is either several LFSRs or a single one, but it has a state, a starting state, initial state, and you call it like that. And if you call capital L the update function, which moves the linear part at some clock cycle to the linear part at the next clock cycle. So in the LFSRs, every bit moves to the right, etc., and there is a feedback. This is a linear mapping transformation, and so you have a linear transformation L here, which is the update function. So if you want to move from the initial state to the ith state, you just have to apply I times L. L is a linear isomorphism. And then you extract in both modals. Once you have the state at time I, you just have to extract a few bits. It's not the same according to the model you've chosen, but in all cases you extract a few bits. This is also a linear operation to choose some elements in a set, in a finite field. And then you apply the function. Okay, so the bit of the current key stream is obtained this way. So maybe I have to make a parenthesis about what is the situation of the attacker when he wants to attack, when she wants to attack the crypto system. She has access to she's supposed to have access to a part of the key stream, because she is supposed to have the whole ciphertext, for instance, and a part of the plain text. And making the sum, she gets a part of the key stream. A part of the plain text, why that? Because she's supposed to have spies or to know that the plain text is a letter and that the head of the letter will be of some form. Anyway, you suppose that she has access to a small part of the key stream and she needs to recover the whole key stream. This is the situation, the model for the attacker. Okay, so we don't have, of course, we don't have this, but we have a few of these. Okay? And so the equations we are interested are those equations where SI is known for some i's and where we are looking for the initialization of the system. Because for the reasons I have not time to present, all the rest of the system must be public. It would not be a good idea to make the function secret, for instance, or to make the feedback of each LFSR secret. So only the initialization is secret, and so we need to recover this from these values. So typically, before Meyer and Courtois, these equations were not, the system of these equations was not solvable because F is supposed to have high algebraic degree. And so each of these equations, this is linear, all this is linear. So each of these equations has degree as an equation in these unknowns equal to the degree of the function. And the degree of the function being large, the system is not solvable because the number of unknowns is huge. It's something like 128, something like that in practice. So when you have a system of equations, even quadratic ones, with many unknowns, it's not possible to solve it. Some crypto systems are based on this difficulty. As I said, highly nonlinear equations with many unknowns. But there is a particularity of stream ciphers is that you can get many equations. You can get many more equations than there are unknowns. You can assume that you have not only 128 equations, but maybe twice or 10 times more. It's, of course, the attack will be weaker, considered as weaker if you assume if the attacker is supposed to have access to a large number of SIs, but if the attack is efficient when taking 1,000 SIs, the crypto system is broken. Okay, so this, to have an over-defined system with many more equations than unknowns, allows linearizing the system, or better using Grubner basis. But even then, the number of unknowns is much too large. But there was this idea, very simple idea by Courtois and Meyer. If you can find a function g which is non-zero and a function h, both of low degrees, such that f times g is h, then you can, from the initial equations, get equations of lower degree. Because, so you start from, you start from this equation. So this is the equation you know. And you multiply by g of L prime, etc. on the left and on the right. So on the left you had SI, you have now SI times g of etc. And on the right you had F, and you get now F times g, that is h, since F times g is h, of this. And so the equations you get here, the unknown, this is unknown. Well, you know g, you suppose you know g, you know L prime, you know L, but you don't know this. You multiply by unknowns, but you get an equation which can have lower degree. You can have f of large degree, but both g and h of low degree. This is this very simple idea which broke many systems, which were considered as previously as efficient. Okay? So this leads to the notion of algebraic immunity. You need the function f. So this is a new criterion of resistance. You need the function f not to admit any non-zero function g of low degree and h of low degree also, such that f times g is h. And there has been a study on these conditions, and at Eurocrypt 204. And finally, a necessary and sufficient condition for the existence of such low degrees function g and h is, and such that fg is h, is that there exists g non-zero of low degree such that either fg is 0 or f plus 1g is 0. It's equivalent to have these functions of low degrees and to have this single function g such that either this or this. And this led to the notion of algebraic immunity. The algebraic immunity of a function is the minimum degree of the non-zero annihilators. This function is called an annihilator of f, and this one is called an annihilator of f plus 1, of the annihilators of f and of those of f plus 1. And this algebraic immunity, to prevent the system from algebraic attacks, needs to be large, needs to be high. What does it mean high? We need a bound to know what is high and what is not. The bound is that, of course, the algebraic immunity is always upper bounded by the degree. This is because f is an annihilator of f plus 1 and f plus 1 is an annihilator of f. But what Courtois-Meyer found, and which made the all stuff about their algebraic attacks, which was really the big new, it's that the algebraic immunity of a function is always upper bounded by the ceiling of n over 2. While the degree is upper bounded by n, the algebraic immunity is upper bounded by half of it. And this allowed breaking many systems. And after that, Courtois found a variant of the algebraic attack that he called fast algebraic attack, in which you don't need necessarily h to have low degree. If g has low degree and h has not too large degree, but can have larger degree than g, and fg equals h, then the attack is also feasible, but it's a version in which you need to take many equations to make one of lower degree, and so you need many more data. It's slower in a way. It's called fast algebraic attack, but if you use the fast algebraic attack when you could have used the algebraic attack, it will be slower. But it's faster when the standard algebraic attack is not working. Okay? But you need more data. Okay, so at that time, in 203, we had to build new functions. The situation for people working on Boolean functions was completely renewed. And quite a few people stopped working on them, in fact, at least in the framework of crypto, because everything had to be done again because of this new criterion, the algebraic immunity. And so people began to try to find functions with high algebraic immunity, hopefully optimal algebraic immunity, and they found first the majority function. In fact, this was finding again something known, because it's possible to see that the algebraic immunity is related to the capacity of correction of a code over the erasure channel. So this notion of algebraic immunity had been already studied by people working on the erasure channel in coding. And they had so exactly the same problem of finding functions with high algebraic immunity, and they had found the majority function, the well-known majority function, f of x is 1 if the weight of x is larger than or equal to n over 2. You can put strictly larger here, it will not change the algebraic immunity, it's easy to show. And Dalai and Maitra and Gupta found this function again, showed it to have optimal algebraic immunity. They found also an iterative construction, very complex. It's very impressive that they could build such function and show it can have high algebraic immunity, optimal one. But the problem is that, as I said, in crypto, you don't need to find functions achieving good parameter for one parameter, but for all parameters. And the other parameters were bad. The functions were balanced, okay, but they had bad nonlinearity and also bad resistance to fast algebraic attacks. So they cannot be used in crypto systems. And at that point, in 2005, stream ciphers using Boolean functions were dead. There were no function to use. We had to find something. Okay? And so there has been first attempts to find functions based on this majority function, increasing the nonlinearity. It was possible to increase it a little, but not enough. And so in 2008, we had nothing. And with Kuching Feng from Tsinghua University, we studied on a function that they had studied there. And this led to a function which is pretty efficient. So the idea of the function is that it's viewed as over the big field, and it's given by its support, which is a string of consecutive powers of a primitive element. And the number of these powers is chosen so that the function is balanced. Okay, so the length of this string is 2 to the n minus 1. Okay, it's half of them. You have the non-zero elements in the field which are in a circle. You can see them in a circle, and you take half of the circle for the support of the function. And magically, this function has optimal algebraic immunity. And the magic is comes from coding, because when you try to find that this function has no annihilator of degree strictly less than n over 2, or the ceiling of n over 2, you can do it by using the BCH bound. See, it's, for someone who is interested in crypto and in coding, this was heaven. That the BCH bound gives the direct solution to the problem. And in addition, this function had good properties. It has optimal algebraic immunity thanks to the BCH bound. It has high algebraic degree, n minus 1, so you consider the univariate representation, you study the maximum 2 weight of the exponents with non-zero coefficients, and you get n minus 1, very good. For the nonlinearity, we could prove a bound, not this one, because this one is an improvement of the first we found. And the bound means that the nonlinearity is considerably better than for the previous functions, but it's not yet enough to use the function. This nonlinearity would not be good. But we run computers up to n equals 28, and we saw that the bound is far from the actual values. The actual values are very good. The nonlinearities of this function are very good, while the bound we can prove is not very good. And there's a gap here. And I know that because I discussed with people working on sequences that they have the same problem with the sequences when they consider the cross correlation. But I don't know. I'm not a specialist. But special cross correlation between some sequences. They observe that when computing it, it's good, and the only bound which can be proved is far from the actual values. So here we have an open question: how to prove that the nonlinearity of the function I've introduced is in fact good while using Gauss sums and standard method leads to the best we can have is what we found with a student of mine called Deng Tong. It's there and it's not sufficient for using the function. But in fact, the nonlinearity is quite sufficient for using the function. And the values computed, so this is what I said, computed to, I've put 24 but it's 28, are good. And the immunity to fast algebraic attacks are good. So we just check this with a computer. But since then, there has been a nice paper which will appear in AsiaCrypto this year, which is completely devoted to the resistance of our function to the fast algebraic attacks. And it happens that the resistance is, for some values of n, optimal. So it's a very good news also. So this function is very good for all parameters. So these are the people for the paper at AsiaCrypto. And so there was also an issue about this function: is it fast? Is it fastly computable? And when you look at the function, if you come back to the function, to know if f of x is 1 or 0, you need to know if x is a power among these powers, then it's 1, or if it's among the other powers. The complexity of determining whether your input is in this set or the complementary is equivalent to the complexity of the discrete logarithm, because you need to know what is you have your input in some form, and you need to put it in the form alpha to the power, to some power, and then you know if the power is among these ones or not. And this is the discrete lob problem, and we know that the discrete lob problem is very hard. But we are in a situation which is quite different from the standard discrete lob problem, because n is small. In the discrete lob problem, n is hundreds. Here, n is at most 20. And for instance, for n equals 20, it's possible to show that Pauling-Hellman method, which is well known, works perfectly well. You can design the function with 40,000 transistors, and it will output 1 bit per cycle, and that's good. That's not the best possible, but that's good. So it's a fast function. So we finally have a good function. But we have only one function. So it's clearly not enough. And after 208, we had to find further functions. And what happened? I have still 10 minutes?
Yeah.
Okay. What happened is first that two Chinese called Tu and Deng used the function I've presented to build another one. The idea was very standard in Boolean functions. It's an idea from John Dillon for building band functions, for instance. Instead of one input, you take two inputs. So the input will be of length 2n, since x has length n, and y has length n also when they are viewed as vectors. But here they are viewed in the fields. And the output to the new function is the output to the previous function, but over x over y. Division in the field. Of course, you cannot divide if y is 0, but in the field, when we're dividing by y is in fact multiplying by y to the 2 to the n minus 2. So if y is 0, the output of x over y will be 0. Okay? So we have this convention. And they could prove that up to a conjecture, which has been checked for plenty of n, up to n equals 31, I think. So for crypto, it's perfect. It's okay. It's proved. I mean, for crypto applications, it's not a conjecture, but it's a fact. But the conjecture deals with all values of n. They could prove that this function has optimal algebraic immunity. So since it has 2n variables, the optimal algebraic immunity is n. And this conjecture is still open. Many people have worked on it. I've received, as a reviewer, quite a few papers submitted who solved the conjecture, but each of these papers contained a flaw, so it's still open. It seems to be quite difficult. Quite a few people have worked on it. So it's an interesting problem. If you're interested, I can send you the conjecture. But you must know that many people have tried to prove it yet until now. The nonlinearity of the two-Deng function, so remember this function, the nonlinearity where f is the previous function, the function which is now called Carlet function. And the nonlinearity is optimal. The function is bent, in fact. But the function is not balanced. So you need to modify it a little to get a balanced function. Okay? So the way of modifying it is here. It's when y is 0 that you modify a little the function. And with this function, you get a balanced function with optimal algebraic immunity and very good nonlinearity. So this function seemed to be much better than the previous one. It seemed to be an improvement. Unfortunately, this function is weak against the fast algebraic attacks. So I first showed it in the ePrint archive, and Johnson and Wang showed a general result which explains why not only this function is bad, but also all the functions which could try to modify, all possible modifications, slight modifications would be also weak. So the idea of two-Deng seems to be not efficient. And so we still had one function. But we have more. So with this same student, Deng Tong, and his supervisor, we tried something too easy, but the kind of thing normally which does not work. We tried, instead of making the division, we tried to make the multiplication. And it works. It's really astonishing. So up to another conjecture which has been proved, because the work which had been done for the previous conjecture and which did not work for the previous conjecture works for this one. We can see that this function has algebraic has optimal algebraic immunity, n. It has almost optimal algebraic degree. And its immunity to fast algebraic attack, which is, it's very difficult to check it, we could go up to n equals 8, is good. So there are good hope that it's good in general, and maybe these people at TesureCrypt will prove it's good. They are on the way to do it. Maybe they've finished. It's possible that it's already done. And for the nonlinearity, we have the same situation as for the Carlet function. The nonlinearity is good, but all that we can prove is a Lau bound which doesn't say it's good. So we have the same kind of gap. There seems to be many functions for which what we can prove mathematically on the nonlinearity is far from what can be calculated, computed with the computer. There's something there, some property, probably of the strings in finite fields, which is unknown, is there, I guess, and we don't see it, and would allow to prove that the nonlinearity is good, while this is not good. And this function is not balanced, but again, just as for the two-rank function, we can modify it so that it's balanced. So it's a little complex. It's a bit technical. I guess you don't have to read this. Just know that it's possible to slightly modify it such that it's balanced. It's even possible to have it one resilient for those who know what is resiliency. So it's a second function. The algebraic degree and algebraic immunity has maximal. The algebraic degree, I said it, is maximal for balanced functions, and there is optimal algebraic immunity. So I've said that. This is said also for this. Yes, this is for the balanced function. I said it only for the original function. Okay, so the two-rank function has been further generalized. So we have proposed a conjecture with my student, which includes the original conjecture by two-rank and also the conjecture we had when we found this function, this conjecture. And this has led to a slight generalization by Jin, Liu, and Wu, proposing new functions, but closely related to this one. And so now we have a few functions. I wouldn't say quite a few, but a few functions, 3 or 4 functions, which are good. And we need more. So if you are interested, welcome to the team. And I finish by the table of the nonlinearities. Of course, it's too small for you to see it, but it shows, you will have the slides if you're interested. It shows that for some values of n, the best nonlinearity is achieved by the Carlet function, and for others, it's achieved by the other function, the function that we propose with my student. Okay, so there's not a function which is better than the other. It depends on the number of variables. So my conclusion is that there is need for more work on Boolean functions for stream ciphers. We were in a very bad shape 10 years ago. We are in a slightly better shape, but we need more work. We need to find more functions. This was the situation in 2003 when algebraic attacks arrived. We had many constructions. In particular, we had secondary constructions, that is constructions of new functions for previously known function, and we don't have such positive situation now because of the algebraic immunity. So I think there should be many more people working on this subject, because most of the people are Chinese working on this. And it's actually a problem for reviewing, because it's young Chinese, it's PhD students, so they cannot review their own papers, and we are always having difficulties to find reviewers for these papers, and this is the proof that there's something going wrong. And we have the same situation for S-boxes also. Too few people working on it. So if you want to join the team, you're welcome. Thank you very much for your attention.